Now that you understand why we need batteries in off-grid systems, it is time to learn a bit more about some important characteristics about batteries. The learning objective of this video is to understand some parameters that we use to characterize batteries. These parameters are important to be considered when choosing a particular type of battery for a PV system. Also, some of these parameters will be used later in the course while designing a PV system with batteries. Let's start with the voltage rating of the battery. The voltage at which a battery is rated and is supposed to operate is called the nominal voltage. This is basically the open circuit voltage of the battery. So-called solar batteries or lead-acid batteries for PV applications are usually rated at 12 volts, 24 volts, or 48 volts. But as we saw in the previous video, this voltage may actually differ from the battery's rated value based on its current state of charge and whether or not the battery is charging or discharging. The next parameter is battery capacity, expressed in amp hours or milliamp hours. When talking about battery capacity, the term refers to the amount of charge that the battery can deliver at the rated voltage. The capacity is directly proportional to the amount of electrode and electrolyte material in the battery. This explains why a small cell has a lower capacity than a large cell that is based on the same chemistry, even though the open circuit voltage across the cell will be the same for both. From this, we can understand that the voltage of a cell is more chemistry-based, while the capacity is based more on the quantity of the active materials used. The third parameter that is used to characterize a battery is its rated current. This is expressed in amperes or milliamperes. This is basically the maximum current that the battery can handle. Currents exceeding the rated current may damage the electrode of the battery. When talking about battery capacity, we saw that it is measured in ampere hours or milliampere hours. Although that change is measured in coulombs, ampere hour is just another unit of charge. Since 1 coulomb is equal to 1 ampere second, 3,600 coulombs is equal to 1 ampere hour. For batteries, an ampere hour is a more convenient unit because of the field of electricity. The amount of energy is usually measured in watt hours. For example, a 10 amp hour 12 volt battery can deliver 1 amp for 10 hours at a voltage of 12 volts. Thus, from the above parameters, we can define the energy capacity of a battery, which is expressed in watt hours. The energy capacity of a battery is simply given by multiplying the rated battery voltage, measured in volts, by the battery capacity, measured in amp hours. For example, a 100 amp hour 12 volt battery will have an energy capacity of 1200 watt hours. Up next is the C rate of the battery. C rate is the measure of the rate of discharge of the battery relative to its capacity. It is defined as the maximal capacity that can be drawn from the battery in 1 hour divided by the battery capacity. For example, a C rate of 1 for a 10 amp hour battery corresponds to a discharge current of 10 amps over 1 hour, and a C rate of 0.5 for the same battery would correspond to a discharge current of 5 amps over 2 hours. In general, it can be said that the C rate of N corresponds to the battery fully discharged in 1 over N hours, irrespective of the battery capacity. To design PV systems, it is also very important to know the efficiency of the storage system. For batteries, usually the round-trip efficiency is used, which is given as the ratio of the total storage output to this total storage input. For example, if 10 kilowatt hours is pumped into the storage system during charging, but only 8 kilowatt hours can be retrieved during discharging, the round-trip storage of the storage efficiency is 80%. The round-trip efficiency of a battery is basically the result of 2 battery losses. Thus, this efficiency is broken down into 2 efficiencies. The first is the voltaic efficiency. It is defined as the ratio of the average discharging voltage to the average charging voltage. In the previous video, we saw that a battery is modeled as a voltage source and a series resistance. This means that the actual voltage of the battery will be different to its open circuit voltage during its discharge or charging process. Thus, during the discharge process, the voltage of the battery will be less than its open circuit voltage. This is because of the voltage drop that occurs inside the battery when current is being discharged. But on the contrary, when the battery is being charged, the battery voltage will be slightly higher than its open circuit voltage. This is to compensate for the voltage drop that occurs inside the battery and to drive the reverse chemical reaction to charge the battery. The next type of efficiency is the Coulombic efficiency, or Faraday efficiency. It is defined as the ratio of total charge extracted from the battery to total charge put into the battery over a full charge cycle. There are always some losses that occur due to power dissipation of the electrodes and imperfect chemical energy conversion. Finally, by combining these two efficiencies, we can obtain the battery efficiency, which we saw a while ago. It is defined as the product of voltaic efficiency and Coulombic efficiency. When comparing different storage devices, this round-trip efficiency is usually considered. Since this efficiency is a product of voltage losses and charge losses, it includes all the effects of different chemical and electrical non-idealities occurring in the battery. I have said before that the voltage of a battery mainly depends on its state of charge. Now, we will learn what this state of charge means for a battery. The state of charge is defined as the percentage of battery capacity available for discharge. Alternatively, we can define the battery capacity in terms of how much it has been discharged. This is called the depth of discharge, or DOD. It is defined as the percentage of the battery capacity that has been discharged. It is basically the remaining percentage that is not included in the state of charge value. The state of charge, or SOC, and depth of discharge values are essentially an important battery parameter that is often used in PV system designing. As an example, consider a 10 amp-hour battery, which has been drained by 2 amp-hours. For this battery, it is said to have a state of charge of 80% or a depth of discharge of 20%. From this, we can see that both terms are complementary to each other. Next, I'll talk about the cycle life of a battery. Rechargeable batteries that are used in PV systems usually undergo many charging and discharging cycles over their lifetime. A cycle lifetime of a battery is defined as the number of charging and discharging cycles after which the battery capacity drops below 80% of the nominal value. Usually the cycle lifetime is specified by the battery manufacturer as an absolute number. However, stating the battery lifetime as a single number is an oversimplification because of the different battery parameters discussed so far are not only related to each other, but are also dependent on the temperature. From this figure, we can see that the cycle lifetime is a function of the depth of discharge for different temperatures. For colder operating temperatures, we can see that a battery has a longer cycle life over its lifetime. Further, the cycle lifetime also strongly depends on the DOD, where it is higher for a smaller depth of discharge. This means that the battery will last longer if the average depth of discharge can be reduced during its lifetime. While the battery lifetime is increased at a lower temperature, there is a downside to this effect. When comparing the battery capacity with its operating temperature, we can see that at lower temperatures, the corresponding capacity is actually lower than that at higher temperatures. This is because the chemicals used in the battery are more active at high temperatures, leading to a higher capacity of the battery. Sometimes, at high temperatures, it's even possible to reach above the rated capacity of the battery. However, such high temperatures are severely detrimental to the overall battery health. This brings me to the end of this video. At this moment, you learned a bit more about batteries and the parameters that are used to characterize them. Later in the course, you will learn how to properly size a battery when designing a PV system. But for now, in the next video, we will learn about another important component in PV systems which use batteries, the charge controller.